All right, now I'm back. So let's talk about the myelin sheath. I told you the myelin sheath acts as an insulator on the axon, so the signal that's being sent from the cell body down the axon to the next cell body goes in a straight line. And we don't want that wandering over. Again, I use the analogy of a lamp cord. You don't want that rubberized plastic coating on the lamp cord stripped off because you grab it and it's touched the bare wires. So that's the same kind of thing that can happen in your nervous system. That's why when I mention babies having unmyelinated nervous system, and sometimes they have kind of odd reactions. The myelin sheath is layers of a plasma membrane of Schwann cells or oligodendrocytes in the peripheral nervous system and central nervous system collectively. So Schwann cells, in peripheral nervous system, oligodendrocytes, central nervous system. Myelination is where neuroglial cells wrap multiple layers of a membrane called myelin around the axon. The lipid content of the myelin sheath insulates the axon, prevents ions from moving in and out, like rubber around a copper wire, increased spread of action potential production. And myelinated axons conduct potentials about 15 to 20 times faster than unmyelinated axons. Cell differences between myelination in the peripheral nervous system versus the central nervous system. The neurolemma, or the outer surface of myelinated axons in the peripheral nervous system, is made up of a Schwann cell, which has a nucleus, organelles, and cytoplasm, not present in the central nervous system. The number of axons that are myelinated. The oligodendrocytes have multiple processes that myelate multiple axons in the central nervous system. A Schwann cell only myelinates one axon in the peripheral nervous system. Timing. Myelination begins early in fetal development in the peripheral nervous system, later, much later in the central nervous system, and there is very little myelination in the brain of a newborn. And there again is the cell body. There's the myelin sheath. Each one of these little structures is a myelin sheath. The nodes or nucleus, excuse me, these are Schwann cells. So this is peripheral nerve system. These little gaps are called the nodes of Ranvier. You have the Schwann cell beginning to myelinate, starts to wrap around, and ultimately it becomes fully myelinated with many, many layers. Here's a cross section magnified by a scanning electron microscope 30,700 times. There's the nucleus right there. There's the neurolemma. This is the myelin, the thing that appears green. I hope you can see that color when you watch this video. And then the axon is in the middle. Myelin sheath of the central nervous system. You see here, there's one cell. Here's the oligodendrocytes, and it's sending out little arms that are forming the myelin sheath on multiple sections of the axon, but still you see the same layering pattern in the central nervous system. The axons in both the central nervous system and the peripheral nervous system are generally longer than the neuroglial cells that are forming the sheath, so multiple cells provide the complete myelin sheath. Each segment of an axon covered by a neuroglia is called an internode. So this would be one internode, this would be one, this would be one. And then the gap between the adjacent neuroglia cell where the myelin sheath is absent is referred to again as the nodes of Ranvier. And again, there you see the gaps where the myelin sheaths don't quite touch one another. Small axons in the central nervous system and the peripheral nervous system are usually not myelinated, so they are referred to as being unmyelinated. White matter is composed of myelinated axons, which appear white. Gray matter is composed of neuron cell bodies. They are unmyelinated with unmyelinated dendrites, and they appear gray. When you talk about the brain, in a couple of chapters, we will talk about the white matter of the brain versus the gray matter. But you have white matter and gray matter in all nervous tissue. Here, the yellow represents the unmyelinated axons, where the rest, here's the Schwann cell and the unmyelinated axon. Regeneration or replacement of damaged tissue is nearly non-existent in the central nervous system. It's limited in the peripheral nervous system. Neural tissue can regenerate only if the cell body remains intact. So if you have an axon severed over at this point, this has not been damaged, then it is possible for that connection to be remade, although this repair would be very slow. For the regeneration to occur, first of all, the axon and the myelin sheath degenerate distal to the injury. It's called Wallerian degeneration. Growth processes form on the proximal end of the axon. Schwann cells and basal laminae form a regeneration tube. Single growth process grows into a regeneration tube, which directs the new axon toward its target cell, and the new axon reconnects with the target cell. So here's the severing we saw. This area right here will die. A new regeneration tube will form with the Schwann cells, and ultimately we will reconnect to that muscle. Glialomas and astrocytomas. These are primarily brain tumors. Again, primary brain tumors originate in the brain. Most are glialomas caused by an abnormally high rate of division of glial cells. I apologize for that. I thought I had turned that off. Predisposing conditions, exposure to ionizing radiation in certain types of disease. An astrocytoma is a tumor of the astrocytes. These can range in severity from mild with very good prognosis to a highly aggressive, very poor prognosis. Depending on the tumor type, treatment may include surgical removal, chemotherapy, perhaps radiation, but again, depending on type, age, and general health of the patient. As far as mild to aggressive, I would call that one fairly aggressive. It's collapsing most of the brain. It's actually gone out into the skull, and it started to eat away at the bone as well. I would call that a very aggressive astrocytoma and probably not have a very good prognosis. All right. Electrophysiology of neurons, so the electrical impulses that we see in neurons. All neurons are excitable, which means they can respond to outside influences, and they will be excitable in the presence of various stimuli. These stimuli can be chemical signals, local electrical signals, or mechanical signals. The stimuli generates electrical charges across the neuron plasma membrane. They will be rapidly conducted along the entire length of the membrane. There's two different types of electrical or two different types of electrical charges. There are latent potentials that travel very short distances, and there are action potentials that are, local potentials that travel short distances, and action potentials that travel the entire length of an axon. So again, we talked about membrane potential in a previous chapter. So you have a thin layer of negatively charged ions existing in the cytosol of the neuron here. You have a thin layer positively charged on the outside. So there is a electron potential, that's the resting potential. Voltage is the electrical gradient established by the separation of charges between the two. The electrical potential across the cell membrane, the source of the potential energy is referred to as the membrane potential. And typical membrane or typical neuron has a resting potential of -70 millivolts. The resting membrane potential is slightly negative because leakage channels favor gradients where more potassium leaks out than sodium leaks in. So there are more, because simply there are more potassium channels than sodium channels. The resting membrane potential of a neuron is less negative at 70 or negative 70 millivolts than that of a skeletal muscle fiber at negative 90 millivolts, largely due to the number of potassium ion leak channels in skeletal muscle fiber cells. Cell is polarized when the voltage difference across the membrane does not equal zero. So it's here, that's not zero, therefore that cell would be considered polarized. And again, here's our little voltmeter measuring this potential, saying it's a negative 70 millivolts. There's my membrane, extracellular fluid with its positive charges, intercellular or cytosol with its negative charges. There is a video on restore or resting membrane potential you can watch at your leisure. The electrical changes across the neuroplasma membranes rely on ion channels and resting membrane potential. Ions cannot diffuse through the lipid component of a plasma membrane, therefore they must rely on these very specific protein channels. So leak channels are always open, continuously allow ions to flow down the concentration gradient between the cytosol and the ECF. So you have, again, potassium and calcium and sodium channels. Gated channels are closed at rest, often in response to some specific stimuli. So a leak channel is one that's always open. A gated channel, one that must be opened when it is needed. The ligand gated channels, which we've talked about before, open in response to the binding of a specific chemical called ligand to a very specific receptor. Voltage channels open in response to changes in voltage across the membrane. And then mechanically gated channels, here's a new one, open or close in response to mechanical stimulation such as pressure, stretch, and vibration. Again, here is the ligand gated channel. They are closed, ligand binds, opens the channel. Voltage gated, it's closed. You have a change in voltage which opens it. And you have mechanical or some sort of mechanical deformation and opens that to allow the ions to move. Ions moving against the electrochemical gradient move via ATP consuming pumps. Again, one of the most important ones, we've mentioned it before, the sodium potassium pump using the enzyme ATPase. Again, if you'll recall from the discussion of muscles, the sodium potassium pumps moves 3 sodium ions out of the cell and then pumps 2 potassium ions into the cell. And that's for each ATP that gets used up. This helps maintain a high concentration of sodium in the extracellular fluid and a lower concentration in the cytosol. And the opposite is true of potassium, so it keeps a low number in the extracellular and a high number in the cytosol. Cells start with a negative resting membrane potential, negative with respect to the extracellular fluid, that is. Unequal distributions of ions across the plasma membrane exists. Gradients are maintained by the gated channels and the pumps. When the gated channels for a specific ion opens, that ion will flow in the electrochemical gradient into or out of the cell. Again, following the gradients. These types of movement can alter cells' membrane potential by opening gated channels and causing ions to flow into or out of the cell. This figure that I'm going to show you in just a second shows a membrane at rest when it's not being stimulated. Then the second one is going to show a ligand-based gated cation. Cations are positively charged. And cations such as sodium follow the electrochemical gradient into the cell. When the cell returns to its resting potential, repolarization has occurred. Again, the third image will show the ligand binding to a cation channel and then that cation channel closing. As the cell loses its positive charges, the membrane potential becomes more negative, and we will return to our resting potential. So Here's the first A showing equal numbers of positives and equal number of negatives at that negative 70 millivolts. Now the ligand that's attached, these positively charged particles are now funneling in, creating a much more positive area over here than over here. And you'll notice we've gone from 70 to, that looks like 60. So the voltage is going down. Then the ligand gated cation starts to move this way. The ligand anion starts to move, and we go back and we're actually going the other direction. So hyperpolarization. We're now more negative than we were at our resting potential. Local anesthetics such as lidocaine, which are commonly administered for surgery and dental procedures, produce temporary numbness in a specific area. How do they work? They block the voltage-gated sodium channels of the neurons in the treated area, thus prohibiting depolarization. The action potentials relaying pain are then not transmitted to the central nervous system. They are non-selective. They also affect sodium channels in the muscles of that area, causing temporary paralysis. That's the reason for crooked smiles and drooling following dental work. You go to the dentist, they do a little work on you, and you come out of the dentist and saw your face down like this, and you can't talk, and you're drooling, and you spit, and you slobber, and everything. That's because we're not only blocking the signals for pain, we're also blocking the nerves that control muscles. Local potentials are small local changes in potential of the neuron's plasma membrane. Triggers long distance action potentials may cause one of two effects, either depolarization, where positive charges enter the cytosol, makes the membrane less negative. Hyperpolarization, either positive charges exit or negative charges enter, which makes the membrane potential more negative, as the images showed a minute ago. Sometimes these are called graded potentials. They vary greatly in size depending on the degree of change in the membrane potential, the number of ion channels open, and the types of ion channels. These can be reversible. When the stimulus stops, the neuron quickly returns to its resting potential. They can be decremental, which means that as changes in the membrane potential are produced or small, the current is lost across the membrane over a few millimeters, cannot send signals over great distances. And again, these are useful for short-term signaling only, such as local potentials. Again, there's a big picture animation of local potentials on the nerve axons. All right, I'll go through a couple of these review questions. I don't know how many there are. We'll go through these, and then I'm going to wrap it up for the day. So, which of the following is not related to the opening of sodium ion channels? The answer is the interior of the cell becomes more negative. So all of the rest of those things do happen. Which of the following is not related to the opening of potassium ion channels? Potassium rushes into the neuron. It actually runs the other way. Which of the following is true regarding membrane hyperpolarization? May result from chloride ion influx. That's the chlorine ion. All right, I'm going to stop there for today, and I will pick up with some more of this on another day. I will see y'all hopefully next time.